Okay, so my last video cut off because I accidentally hit the button and I really don't have time to start all the way over. So here we go. Just picking up where we left off. We were talking about angular velocity versus linear and how Mr. Ware will oops, that's the eraser. Mr. Ware will travel a longer linear distance than me in the same amount of time. He will travel this distance, I will travel this short distance. So let's define linear velocity then to be the ratio of the distance traveled along the curve of a circle to the time. So imagine if we were to unfold our circle and lay those distances flat, that's kind of more about thinking about miles per hour. It's that distance traveled along that curve to time, so that ratio. The formula for this one, for linear velocity, is going to be, we actually use v for velocity this time. So anytime you see v, it's understood that that is linear velocity, which I'm okay with you abbreviating this as LV if you want. So linear velocity is going to equal r times theta over t, where r stands for the radius of the circle, and then theta obviously stands for an angle, and then t stands for time, but you have already seen theta over t earlier in these notes. If we scroll back up to our angular velocity formula, theta over t is equal to omega. It's equal to the angular velocity altogether. So instead of using this as our theta and radians to t over time, we know that this is the angular velocity. So another way that we could talk about the linear velocity is by rewriting it as v equals r times omega. So you could use either one of these and they would be fine. So you could use this one, r times theta over t, or r times omega. And it just kind of depends on the information that you're given in a particular problem versus which one you may want to use. Although this one's going to be the easier one, depending on if you're given enough information to just plug it in straight away. So let's do an example. I'm going to ask you to find the linear velocity. Again, feel free to abbreviate. Find linear velocity of a point rotating at an angular velocity of 13 pi. I don't know if I can write pi. Oh, I bet I can. Let's see. No, I'm just going to write it. 13 pi radians per second at a distance of 7 centimeters from the center. So find the linear velocity of a point. This should say rotating, not rotation. Rotating at an angular velocity of 13 pi radians per second at a distance of 7 centimeters from the center. Well, what should stick out to you here is the phrase angular velocity, meaning they gave us the shortcut, so to speak, right? They already gave us omega. So we can use the shorter of the two formulas. So if I use v equals r times omega, they give us a radius of 7 centimeters. So then I've got velocity, so this implies that the velocity is equal to the radius of 7 times the angular velocity, omega, which they already tell us the angular velocity is 13 pi radians per second. And then I didn't specify in the directions here, but let's just go ahead and round this to the nearest tenth. If we do so, then that means the velocity is going to be approximately 285.9. Now let's discuss units. Angular velocity is the ratio of the angle per time. So we know every time that answer is going to be radians per, whether minutes or radians per seconds. When we talk about linear velocity, we measure lines in so many different ways, right? We use centimeters, we use inches, we use miles, meters, all kinds of those things. So when we talk about linear velocity, you are always going to answer in some sort of distance unit. So answer in, we'll say, a distance unit, or a linear distance unit. I mean, that's the best way to say it, right? Linear distance unit per time. So in other words, we might answer in centimeters per minute, or inches per second, or meters per minute. Okay? Linear distance per time. So and you don't put radians per second or whatever. So here, our linear velocity, go back to our problem, look at what information they give us. They talk about the distance of 7 centimeters of a radius. Therefore, our velocity is going to be approximately 285.9 centimeters per, we are in seconds, centimeters per seconds of that velocity. Okay, so if we did the problem and we calculated Mr. Ware and I's linear velocities, they should be different because we are traveling, our radius from the center of the carousel would be different, even though our angular distance or angular velocity would be the same. So hopefully that helps clarify between the two. I will be available for questions during class.